If this is my ferromagnetic material, I've got a bunch of tiny little arrows inside. They're not really arrows, right? But we represent them by arrows. Those little imaginary arrows we call domains. Tiny little regions inside a ferromagnetic material. What's a ferromagnetic material? Not something that can be charged. Close, but not something that can be charged. You want to try that again, Maria? Good, something that can become magnetized. Now, there's a whole bunch of other terms. I've seen a question like this before where they mention a term called diamagnetism, paramagnetism. Guys, if you ever see a term like that that we haven't talked about, it's not the answer. Remember that. If you ever see a term that we haven't talked about, it is not the answer. Okay, that might come in handy for you coming up sometime soon. If you haven't seen a term, it's not the answer. So ferromagnetism or ferromagnetic means a material that has the potential to become magnetized. It has these tiny little regions inside it that are pointing in random directions when it's not magnetized and pointing in one direction when it is magnetized. What are the two ways that we talked about where we can align these domains and start pointing them in the same direction? What's one of them? Yeah, bring a magnet nearby. When I bring a magnet nearby, this time I'll bring it over here instead of putting it above like I did yesterday. Bring it to one end, and what happens? We temporarily align the domains inside this non-magnetized ferromagnetic material. So instead of pointing in random directions, we don't necessarily get all of them pointing in exactly the same direction, but at least we get some kind of magnetic effect here because they're more aligned. Now, when I take that object, I was almost going to say, Maria, the charging object, but when I take the permanent magnet away, then these domains are, within a fairly short period of time, going to go back to where they were before. That is pointing in random directions. Okay, if I bring a magnet nearby the leg of your desk, it's going to become attracted. Well, it's going to become attracted because we're temporarily aligning the domains in the leg of that desk. But when I bring that magnet away, then it's not going to take very long for that desk to become non-magnetized again. The domains are going to start pointing in random directions again. What's the other way you can do it? Yep. Yeah, we talked a lot more about that yesterday, wrapping a wire around it and applying an electric current through it. Okay, that's what Ørsted discovered almost 200 years ago. Electric current generates a magnetic field. That magnetic field will magnetize the ferromagnetic material or cause the domains to become more or less aligned in the same direction. Which end of this magnet is north and which end is south? Which end do the domains point to? They point towards the? Good. So this is going to be the North Pole. This is going to be the South Pole. Now we looked at magnetic fields outside of the magnet. Right? The magnetic field outside of the magnet, we said, always goes away from the north and toward the south. Looks like this. We drew a whole bunch of diagrams on that last week when we did a little activity. In the end, you can see that the magnetic field outside the magnet is really just an extension of the domains inside the magnet, right? If the domains go from south to north, then they just continue on and go from north to south on the outside of the magnet. If we're ever talking about the magnetic field inside the magnet, then we'd be talking about the magnetic field going from south to north. But we define the direction of magnetic field as being from north to south, and by default, we mean by that outside of the magnet. Okay, so inside of the magnet, we're going from south to north, but outside of the magnet, which is where we're usually looking at, we're going from north to south. What's the other way that we define the direction of magnetic field? From north to south, and if we're talking about an electric field, we'd say it's the way that a positive charge moves when placed in the field. But here we're not talking about an electric field, it's a magnetic field. So it's the way that, yep, good, the way that a compass will point when placed in the field. So the compass will point toward the south, and that has some implications for us, right? Some pretty big implications. We draw a picture of the Earth. Okay, there's that little imaginary, well, that big imaginary bar magnet that's inside the Earth. The magnetic field that surrounds the Earth looks something like this. Looks something like the magnetic field that surrounds a simple bar magnet. But we notice that the magnetic field points this way, towards what we consider to be northern Canada. That means that because the magnetic field points that way, and a compass points in the direction of the magnetic field, then that means that this must actually be magnetically the South Pole. Geographically, the North Pole, magnetically, the South Pole. Now, how does that affect us navigationally? You're out there in a ship and you're trying to navigate somewhere, and all of a sudden you realize, oh, wait a second, we've had it all wrong. The North Pole is in Antarctica and the South Pole is in Canada. Does that mess us up? It doesn't mess us. It doesn't have to mess us up. Not if we're all agreeing on the frame of reference that we're using. If we all call this north, even though it's not really magnetic north, if we all call it north, then it doesn't really matter what it is. Okay, we can call it whatever we want as long as we're all calling it the same thing. Technically, it's magnetic south, but whenever we're navigating, we call it the north, and everybody goes by the same frame of reference, so it doesn't really matter. I said to the other class yesterday, if you wanted to, when you're navigating, you could call it Bob. As long as everybody calls it Bob, which way are you going? Oh, I'm going Bob. 38 degrees, Bob of west. As long as everybody is under the same understanding of what it is, then it doesn't really matter what we call it, right? We usually call it north. It just isn't. It's really south. But we call it north, and that doesn't need to change a thing. Okay, if you're navigating with a compass, we'll still call it north. Just understand that it isn't north. We should start a campaign, an online petition to rename north Bob. We'll see how far that goes. Probably not very. Let's draw a couple pictures of magnetic fields, and then we'll move on to the stuff that we did yesterday. We pretty much already drew the magnetic field surrounding this, because it's the same as magnetic field surrounding a bar magnet. Which way do the field lines go? From left to right or right to left? From left to right? This way? From right to left, yeah. It's from right to left. Yeah, it's from north to south. Good. From right to left or from north to south there. That's a pretty easy mistake to make, right? But in the end, if you get a question on a quiz or test or diploma exam that gives you this bar magnet and it asks you to, not to label, but to identify which way it's going or to identify the correct diagram or whatever, we got to get this one right. Okay, this is the gimme question that all of us can start off with getting correct, right? That's your 2% head start on your diploma exam, is getting that question correct, okay? Let me draw another one for you. This time I'm going to draw some magnetic fields surrounding these two bar magnets. And I'm going to ask you some questions about it. What do you know about this pole, let's say position 1 and position 2? What do you know about those two positions? Yeah, they're the same poles. Do we know what poles they are, north or south? Do we know that they're both north? Could they both be north? Let me ask another question. There's a couple ways we could ask this. What could you definitively say about those two poles? What could you definitively say about those two poles? Here's a couple of options. They're both north. B, they're both south. C, they're oppositely charged. Sorry, opposite poles. D, they're like poles. What's the answer to that? What could you definitively say, Tom? It'd be D, they're like poles. Okay, we know they're like poles because of the shape of that, but we don't know the direction of the magnetic field there, so we don't know whether they're both north or whether they're both south, right? We know they're not opposite poles. We know they're like poles. They could be both north, they could be both south, but we don't know that for sure. What if I was to do this? What if I was to put a north pole right there? That's the only thing I'm labeling, is the north pole right there. What could you now definitively say about these two? Okay, A, they're both north. B, I was going to say B, they're both south. Well, one is north, one is south. C, I don't know. I don't have any other options right now. A or B? It's A, right? We know they're both north at this point, right? Because they've got to be like poles because of the shape of it, and they've got to be both north because one of them is labeled as north. What about this? What if I labeled one field line right there? What could you now definitively say about those two poles? Emma? They're both south. We know they're both the same poles because of the shape of it. That hasn't changed. Emma, how do you know they're both south, though, as opposed to both north? Good. We know that the magnetic field has to go from north to south on this one, and therefore, if this is going to be the same pole, this is going to be south. Maybe we label some magnetic field there as well. Does that make sense? All right, let's try this one. Let's change the orientation of them this time. Look at that, we're rotating it. Let's see if you can handle this. Okay. We got a magnetic field that looks something like this. Something like that. It's not a very good diagram, but what do you definitively know about these two poles? Okay. They're opposite poles. One's north, one's south. Which one's which? Do we know? No, we don't. No. What if I label that north? What do you now know? Position, let's go position 1, position 2. Here's your question. The polarity at position 1 is blank, while the polarity at position 2 is blank. Option A, north, north. Is it correct? Option 2, or option B, south, south. Is that correct? No. Option C, south, north. Is that correct? Yes, it is. We know this one is south because it's got to be opposite to this one, right? We can't have a monopole. It can't be north-north. It has to be north and a south in the same magnet. And if that's south, then that's got to be north because the shape of this is indicating that they're going to be opposite poles. If we had to draw the field lines in there, we draw them from north to south this way. Does that make sense? Okay, that's basically where our quiz will end tomorrow. Okay, we'll spend a couple minutes right now reviewing what we did yesterday. We'll quiz you on that a little bit later on, okay? Yesterday, we talked about this guy, Hans Christian Ørsted, that almost 200 years ago, 195 years ago now, discovered what I would argue, as he said yesterday, is one of the most important technological discoveries in the history of the world. Because just about every bit of technology that we use today is based, at least in part, on that discovery. That discovery is that electricity produces magnetism. It's as simple as that. Moving electric charges, and that's all electric current is, right? Moving electric charges generates magnetic fields. Okay, moving charges or electric currents generate magnetic fields. What's the shape of that magnetic field? A little bit different than all the shapes that we've drawn over here, right? What's the shape of the magnetic field that surrounds a wire that carries an electric current? One word. I could keep talking about this, but I feel like I'm talking in circles here. What's the shape of the magnetic field here? Circles. Good. Let's go to the examples. These are the examples that we did yesterday, so it's nothing new there. This one represents what? The X represents, which way is it going? Into the page. Let's change it around a little bit this time. Let's make it an alpha particle. Yesterday, these were all electrons, so negative particles. This time, they're going to all be positive particles. So we got a positive particle going into the page. We know the magnetic field that surrounds that is circular. The circles get further and further apart the further you get away from the wire. That makes sense, right? Because the further you get away from what causes the field gets weaker. What's the direction of that magnetic field, though? Clockwise? How do you know that? What'd you do? Okay, she did the hand thing, she said. Okay. Usually we call it the wire grasp rule, but maybe we should call it the wire grasping handy thingy. Okay. I don't care what you call it, okay, as long as you can do it, and you're correct, by the way. Okay, it doesn't matter what you call it. In the end, we take our right hand this time because it's an alpha particle. If it was a negative particle, we'd use our left hand. We stick our thumb which way? Good, the way the charge is going, which in this case is into the page. And then we bend our fingers. Now, I'm bending my fingers just a little bit. Okay, I'm looking around here and I see one or two people bending them just a little bit. Okay, I see one or two people going like this. Okay, it doesn't matter. It doesn't matter how much you bend your fingers, right? Because in the end, if you bend them just like this or like this, my fingers are going, just as Maria said, clockwise. Let's make this one an electron. Okay, let's make this one an electron. We know it's going to be circles again. Which hand? Which hand do we use? It's the left hand, yeah. Left thumb bow is going which way? Good. Out of the page, toward the back of the room in this case here. So we're going to stick our left thumb out this way. Fingers are going clockwise again. How is that possible? We had a charge going into the page. We have a charge going out of the page. They're both producing a clockwise field. Ken? They're both producing a clockwise field? What's the deal with that? Yeah. Good. So opposite charges, right? When they're opposite charges, you're going to produce a magnetic field that's in the opposite direction. So it's kind of like it's almost like the old thing, two wrongs make a right, or two negatives make a positive here. We're switching both the type of particle and the direction of the particle, which ends up giving us the exact same magnetic field. And then finally, we have one over here where we've got an alpha particle, which is a positive particle. It's going to the left of the page. Means we're going to use our right hand. Our right thumb sticks close to the left. My fingers right now are above the wire, and they're pointing which way? What's this? This is technology at its finest right now. If my thumb is pointing towards the left, and my fingers are pointing into the page, okay, then I get a magnetic field that, oops, I should have did that below, right? Because it should be an X actually, right? As opposed to a dot going into the page. Below it, it should be out of the page. In front of the wire, it should be up, and behind the wire, it should be down. If you want to do it in all four positions, that's fine. Or if you want to do it in one position, like this, and then just kind of trace it around like this and determine at different spots which way the field is pointing, that's fine too. It would depend upon how the question was asked. Tom, in all likelihood, if you get a question like this on a test, and I have seen them like this before, it would say, what's the direction of the magnetic field above the wire? It would ask you probably for one position. Okay? Something like this would probably ask you like a clockwise, counterclockwise type thing, right? How about this one? Here's two wires that are actually pretty close together. They both produce a magnetic field. And because they're close enough together, those magnetic fields will interact with each other. They're going to cause either a force of attraction or a force of repulsion. I'm going to give you about 90 seconds to see if you can figure out whether these two wires are going to attract each other or repel each other. It's an A or B answer, right? Okay, it's not none of the above. It's A or B. They either attract or they repel. Let's see what you can do with that, and then we'll take a look at it together. Simon, what did you do to say attract? What's your logic?
Well, I had two magnetic fields that they were going counterclockwise and clockwise.
Yeah.
And they were opposite fields.
Okay. Okay, that seems like pretty good logic. So he says that, let's draw the magnetic field in here. We've got, let's assume we have a negative particle. I didn't say that, but even if it's a positive particle, we're going to get the opposite fields in the same effect, right? So let's say it's negative particles. That's going to cause a field that's this way. It's going to cause a field that's this way. If we keep looping that around, it's going to look like this. And you're saying since those fields go opposite to each other, or that it's going to attract? Okay. Logic seems okay there. What do you say, Bo? You said repel, right? What's your reason for repelling? Is it kind of his logic? Except which gave you the opposite answer. Okay. Anybody else want to elaborate on that a little bit? Okay, here's the moment of truth. Simon, your logic was good right up until the end. I'm going to pretend for a second. You don't have to physically draw this in, but sometimes it's helpful to do this. I'm going to pretend we got a little bar magnet here and a little bar magnet here. Okay, this is just going to help me visualize it. If we had a bar magnet right here, then this would be a south and this would be a north, because the magnetic field outside would go from the north toward the south, and the magnetic field on the inside would go from south to north, right? Here, we've got south and a north. If we had a bar magnet there, it would be a south and a north pole. Take a look at those two magnets. Are they going to attract each other or repel each other? Both? They're going to repel each other because it's north against north, right? So because they're going in opposite directions, they're going to push each other apart. Okay, so again, your logic was good. It's just your conclusion was a little bit flawed there, right? Now, somebody might say, well, what if I drew the magnet up here? That would be north over here and south over here, right? Well, yeah, it would, but it would be south over here and north over here. They'd still repel each other. What if I drew it right here? This would be north and this would be south. This would be north and this would be south. They'd still repel each other. In the end, again, you don't have to draw in the magnets. All we have to do is look at the fields and say, look, they're going towards each other like this. They're going to repel each other. Okay, if we looked at two magnets, no, that's bad. Never mind. That's just going to confuse you. So these two magnetic fields are coming towards each other or away from each other, as they are at the top there. Then it's got to repel. Okay, got it? Now, what a lot of people do is say, okay, I'm just going to memorize that now. I'm going to memorize when the charges are going in opposite directions, then that's going to give me a force of repulsion. That means if they're going in the same direction, it's going to give me a force of attraction. Don't memorize it. You don't memorize anything like that. If you can figure it out, the only thing you should memorize is things you can't figure out. If you can figure it out, then figure it out. Hey, what if we change things up just a tiny little bit and all of a sudden you're kind of hooped? Okay. All right. Yesterday I left you with worksheet number 5, and I think that we finished up worksheet number 5. Are we okay with that, or is there anything we need to go over with that? We're good? Or not worksheet number 5, but worksheet number 10, I guess it was. All right, we're going to give you a couple of applications here right now. The first one is, what is this? Speaker, right? How does a speaker work? You ever take apart like the speaker in your car, or install a speaker in your car, or take apart the speaker from your stereo system at home? Even really like your iPhone earbuds or whatever, it's the same thing. It's just much, much smaller and much, much harder to see. A speaker consists of a cone that's like a felt-type material, and it vibrates back and forth. Sound is generated by compressions and rarefactions in air, pressure differences within air. So all you have to do is move something back and forth, and you cause sound. And how quickly you move it back and forth determines what sound exactly it is that you hear. So if we can move this cone, this felt-type cone material back and forth at the rate that we want to move it back and forth, then we can generate the sound that we want to hear. So how do we move it back and forth? Okay, well, you can take your hand and push it back and forth, but that's not going to go back and forth at the rate that we want it to. It's not going to generate the sound that we're supposed to hear. So what do? We send an electrical signal to it. The wires that go to your speaker carry an electric current from your stereo or from your iPhone or from your whatever. That electric current is related to the music that was being produced. So the music is converted to an electrical signal. That electrical signal goes to a wire here. It goes to a wire right here. And that wire is wrapped around a piece of steel or some kind of ferromagnetic material. Wraps around, comes back right there. What's going to happen now? How does this work? As an electric current goes through the wire, what does it do? What does it do to that piece of steel that's that's right here that's attached to this cone. It magnetizes it, right? So what? So what? So it magnetizes it. So what? Well, if it magnetizes it so that the one end of it is oppositely poled. I'm not sure if you can say that. Okay, opposite poles to this permanent magnet here, then it's going to attract that piece of steel inwards. That's going to pull the cone with it and create a low pressure zone of air. If it repels it, because the current is flowing in the opposite direction, then it's going to push it out. Okay, so it's going to go out here. It's going to be repelled by the permanent magnet, and that's going to push the cone out as well and create a high pressure zone in the air. So by changing the electric current, which is going to be related to the music that you're trying to send out there, the current would be proportional to the sound, then that gets replicated in the cone going back and forth at the same frequency as the music was being generated. That means that the sound at the other end of it over here is going to be produced at the same frequency as the cone was vibrating back and forth, which is the same frequency as the charges were going back and forth on the wire, which is the same frequency as the original music was that was coming out of your stereo. Yep. How can you blow a speaker? Well, if you got too much energy here, you get too much electric current going through here, right? Which means you turn the volume up too high, right? We're not talking about the frequency. When you turn the volume up high, you're not changing the frequency of what was generated. Okay? So you turn the volume up too high, too much current going through there, too much magnetic field strength being generated by this wire, too strong of an attraction or repulsion with this piece of steel and this permanent magnet. And at some point, maybe you've caused so much repulsion or so much attraction that you actually tear this cone. It's pretty soft, like say felt-like kind of felty, cardboardy material. So it's not all that hard to actually tear it. Okay, if you pull it back too hard, okay, with your hand, you'll rip it. If you pull it back too hard by a magnetic force, then you'll rip it as well. Yep.
It attracts and repels the level of air.
Well, it attracts or repels to create high pressure areas and low pressure areas in the air. Sound waves, if you remember from physics 20, sound waves are what we call longitudinal waves. So it's not like the water wave that you see in the ocean, right? That's a transverse wave. The longitudinal wave is that series of compression and rarefaction, right? High pressure, low pressure, high pressure, low pressure. So by moving this cone back and forth, okay, at different rates, we're generating areas of high pressure and low pressure. We're generating longitudinal waves with changing frequency, which is exactly what we want, because music isn't one constant frequency, right? So the wave that we generate by moving this cone back and forth at different frequencies ends up replicating the music that was produced in the stereo in the first place. Does that make sense? I got one more for you. By the way, guys, just like when we talked about electrostatic painting and what was the other example that we gave with that? The electrostatic precipitator, the air filter. Right? The odds of you seeing this example, this application on a test are pretty small. It's not zero. Okay? I mean, they could pick this example. If they did, we'd be lucky, because in all likelihood, you know, there's a million different examples that they could pick. Right? There's a pretty good chance they'll pick something that illustrates what we're talking about here. Okay? But it's probably not going to be this. In the end, if you can follow the logic of what we're doing here with these examples, then you should be able to follow it with new examples as well, even ones you haven't seen before. What's this one? Everybody tell me what that is? It's a bell. Okay, so what kind of bell? Where would you see this bell? Okay, a school bell, like one of the old style school bells that, you know, that signal the end of the day, or maybe even a fire alarm, right? A doorbell, like an older style doorbell in a house. Okay. How does this work? This is kind of neat, actually. You can see a switch up here which turns on or off the current that's generated by this battery. This battery has a negative end and a positive end like this. That causes the electric current to flow this way. So it causes it to flow counterclockwise. As this current flows through this piece of steel right here, it hits this thing that we call a make-break contact. A make or break contact. Right now, it's being made. If the switch is closed and the current is flowing, the contact is being made. So electrons end up flowing through here, through here, through this. I don't know if you can see this little spot right there. Okay, through here, around here, and then back around here. So the complete circuit is formed. Electric current is flowing. What does that do? How does that cause the bell to ring if the circuit is completed? If I flip on the switch, the bell rings. But how? Devin? Okay, so these electromagnets, you mean? So as the electric current flows through these wires right here, that's going to magnetize some kind of steel core or iron core that's inside those, cause electromagnets, and that's going to attract this thing right here. Is that what you're saying? Okay, which is attached to the hammer. So as it attracts that, pulls it down towards these electromagnets, pulls the hammer down towards the bell, and what do you hear? Ding. Well, that's not much of a fire alarm. The fire alarm in this room, by the way, if it ever goes off when we're in this room, it's not very loud. Okay, if I'm talking or playing a movie, we're lucky if we hear it. Okay, we'll just have to run outside the building if we see everybody screaming in terror running by the room. But if it's just one ding, we're definitely not going to hear it, right? So Devin, how does it go ding, 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 ding? Okay, so this make-break contact point right here is now broken. So we want to have electric current go here, we want to go through to here, but now it doesn't because that's broken. So if it's broken, what happens? So the electromagnets aren't electromagnets anymore. This little spring right here pulls the hammer back. Electric current's not flowing, right? When it pulls the hammer back, what happens? Contact is made again. Current starts flowing, repeats the process. So when the switch is closed, the current starts flowing, the electromagnets attract that piece of steel, the hammer hits, you hear a ding, that breaks the contact, everything shuts off, spring pulls it back to where it was before, makes contact again, repeats itself. So if you have current going through there at 60 hertz, 60 cycles per second, which is the current that's in our wall, then what ends up happening? We end up having this thing going back and forth 60 times per second. So we end up hearing ding, 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 right? Which is our fire alarm, or an old style doorbell, or an old style school bell signaling the end of the day. Does that make sense? These are two pretty basic applications of Ørsted's discovery that he made 195 years ago. Okay, but you can see that even in the most basic things, his discovery is pretty pivotal. Okay? And as I said yesterday and earlier today, in most of the technology that we have today, it's used somewhere. The idea of electricity generating magnetism. All right? Let's take a look at one more rule here right now. I want to take a look at actually two more rules, but one more rule quickly here. We call it the coil rule for solenoids. A solenoid, by the way, is just a coil of wire. So it's what you see in the picture here. Wire wrapped around something is a solenoid, a coil of wire. A bunch of loops going around something. Now, in your textbook, they call this the wire grasp rule. Well, I'm not going to call it the wire grasp rule because we already have a wire grasp rule. And it's not the same thing. In fact, it's exactly the opposite. The purpose of the coil rule for solenoids, or the coil rule for coils of wire, the purpose of that is to determine what the polarity of an electromagnet has become. So you wrap wire around something, apply an electric current through that, then it produces a magnetic field, and that causes this thing to become an electromagnet with a north pole and a south pole. But which end is north and which end is south? Remember in the wire grasp rule, your thumb pointed in the direction of the moving charges, and your bent fingers pointed in the direction of the magnetic field. This time it's going to be opposite. Your thumb is going to point in the direction of the magnetic field, right? B, the magnetic field, and your bent fingers will point in the direction of the moving charges. So it's exactly the opposite. Here's what I'd like you to do right now. Take a piece of scrap paper, okay, whether it's out of your book or whether it's from the side of the room right there, it doesn't matter. Just take a piece of scrap paper and roll it up like this. This is your solenoid. This is your solenoid. This is your coil of wire. Now, you can see in this picture that's up on the board right now, the electric current is such that it's going up in front of the coil, and then you can see it kind of loops back down in the back. Up in the front, down in the back. Up in the front, down in the back. Do you guys see that? So we're looking at this vertical plane here. The plane of the page is right here. The current is going up in the front and down in the back. You can see that by the arrows on this coil right here. It's going up in the front, and then it's going to go back down in the back. And up in the front, then back down in the back, and so on. What I'd like you to do is take your fingers, your left hand, because we're dealing with the electrons going through this wire. And I'd like you to stick your fingers either up in the front or down in the back. Doesn't matter, because the electrons are going up in the front and they're going down in the back. Okay, just make sure that you pick one and go with it. So remember, you're looking at your fingertips, your fingernails, okay, that we should paint arrows onto with fingernail polish. That's what we should do on Friday, lab day. Our lab is paint our nails with little arrows. Fingers up in the front. Okay, everybody do this right now. Okay. Have your paper perpendicular to you. Okay, and remember, the part of the page that you're looking at is the front. Okay, right now I'm looking at the back of mine because I want you to use your frame of reference here. Okay, this is the front of the paper. Okay, if I'm looking this way, this is the front of my paper. This is the back of my paper. So I want you in front of your paper to stick your fingers pointing up. Or, no, yeah, right there. No, turn around. Yeah, there you go. In front of that paper, your fingers are pointing up right now. Okay? In front of the paper, your fingers are pointing kind of this way. That's okay, though. Turn that around. Okay, turn it around. So in front of the paper, your fingers are pointing up. Right? Okay, so that's good. That's good. Okay, yours are pointing down, but they're in the back, so that's okay. Okay, same thing. Down and in the back is okay. Okay, that's okay as well. Okay, we're either going up in the front or down in the back. Okay, I think everybody's got this, has got it here. Which way is your thumb pointing? Which way is your thumb pointing? To the right. So that means the magnetic field there would point inside the coil to the right. That means it would continue on outside, point this way. What's the polarity of this then? If the magnetic field points towards the right inside the coil, then this has got to be a north and this has got to be a south. So the right side of the electromagnet that you just made is a north pole. The left side is a south pole. Make sense? Okay, let's try another one of those. You got a piece of steel here inside a coil of wire. Here's your battery. This is the positive end of the battery. This is the negative end of the battery. The electrons are going like this, counterclockwise, up in the back, down in the front, up in the back, down in the front, up in the back, down in the front, and so on. Again, take your piece of paper, coil it up. It's your new solenoid or your new coil of wire. Your fingers should now go down in the front or up in the back, it doesn't matter. Which way is your thumb pointing if your fingers are going wrong way? No. Turn your hand around. No, because your fingers here, Caitlin, are still going. There you go. Yeah, because we want them to be going down in the front, right? Okay, you're looking at your fingers. You're looking at the front of your fingers, right? Which way are they pointing? Okay, good. So down in the front. Which way is your thumb pointing? Which way is your thumb pointing, guys? To the left. So the magnetic field inside this coil is to the left. That makes this end what? Right, remember the magnetic field outside goes from north to south. Inside it goes from south to north. Is that okay? Yep. Yep. How about this one now? We don't actually have to have something that's ferromagnetic inside, but the effect is magnified if we do. So usually when I draw this, I draw a piece of steel or a piece of iron or something inside. But if it's not there, the same analysis applies. Okay, don't get thrown off if you see on an exam a coil of wire without a piece of steel or something ferromagnetic inside. Same thing applies. Again, it's just not quite as pronounced of an effect. That's all. Not as strong as the electromagnet. So there's my iron core or steel core. Here's my coil wire here. Looks like this. Which end is positive? Which end is negative? This one is what? That's positive. This is negative. You know how I remember that? Years ago, I remember when I first started teaching here, my first year here, which was 20 years ago, there was one other science teacher at the school. He taught chemistry and biology. And I remember one day he came over to my classroom. So it was two of us. He came over to my classroom. He was doing something in chemistry, and he had forgotten. He says, I'm drawing these batteries for my kids. And he says, I always forget which end is the positive end and which end is the negative end. I always forget that, right? So how do I remember that this is positive or this is negative or whatever the case may be? Well, the way that I remember it, and you can't really go wrong on this, is that, look, the longer line, the longer vertical line is the symbol that has a vertical line in it. Right? That's the positive. The negative one, the negative terminal here, is the shorter vertical line. It's the one that has no vertical line in it. It's just a negative symbol. So the long one is positive, the short one is negative. That means the electrons are going to go counterclockwise again, just like they did in the last one. Up in the front, down in the back, up in the front, down in the back, and so on. You take your piece of paper, your coil, roll it up. Your fingers, remember, in the wire grasp rule that we learned yesterday, it was thumb current, fingers field. In this one, it's fingers current, thumb field, exactly the opposite. My fingers right now, in front of it, guys, you have a tough time where to put your fingers? Okay, look at your coil right now. You're looking at the front. Don't worry about clenching your fist right now or bending your fingers or anything. Put your fingertips right on the front. Just do that. Just put your fingertips right on the front. And then bend your hand. So my fingers are pointing up in the front, or I could have went down in the back like this. And then when you look at it, though, which way is my thumb pointing? To the right. That means the magnetic field inside this coil is going to point this way. That means that this end is the, which end? South end, and this end is the north end. Is that good? Wait a second, though. Look at that last diagram we drew. We had the exact same setup, right? Okay, the current is flowing counterclockwise, just like it is in this one. Counterclockwise. But wait a second. South and north in this magnet? North and south in this magnet? What's the difference there? Why did we get opposite polarity when the current was going in the same direction? Yeah, exactly. The current here was going down in the front. The current here was going up in the front. So it's the way that the wire is wrapped around, right? If you take a really close look at this spot right here, that first loop goes behind the magnet, whereas here the first loop goes in front of the magnet. So although the current is going counterclockwise in both cases, it's effectively going in the reverse direction around the piece of steel, which causes the opposite polarity. You still comfortable with that? You need one more example, or are we good there? Okay, we'll stop it there. We'll start off tomorrow with a little quiz. Remember, not on the hand rules, just on basic magnetism stuff. And then we'll, after the quiz, do another one of these as a practice and see where you're at. See if you can do it yourself. Okay?